Alrighty, gang, welcome back and good morning. Today, we are going to continue where we left off last time, which was the little introduction to power series. Hopefully you are enjoying the little bits of power series stuff we have learned. Today, the work really begins. So let me see. Yeah, I haven't given you any fresh homework on this stuff. So you're going to have your first homework to do with power series opening up today, and it'll have plenty of 11.8 stuff that we talked about last time. Let me come in here and just get started. I'll remind you where we are. First, of course, this is MAC2312 section 004, which is Calc 2. And today is the 8th of November, 2021. I have not finished grading your tests. My goal, as always, is to get them back to you a week after you take them. I still need to collect some of the tests from the testing centers, so we will be moving forwards with that stuff, and I'll do my best to get them back to you by Wednesday. If you took the test at the testing center, took the makeup test, it might be a little bit longer. But today we're going to continue with power series. So I'll begin by saying recall. A power series is an expression of the form sigma n from 0 to infinity Cn times x minus a to the n. The Cn are called the coefficients. A is called the center. And associated with each power series are two objects which we want to find. Two objects which we need to find: the radius of convergence which is the number we usually call capital R, and the interval of convergence, which is always one of open A minus R to A plus R, left closed, right open, A minus R to A plus R, left open, right closed, A minus R to A plus R, or the fully closed interval, A minus R to A plus R. It's always of that form, right? So it's always an interval that's symmetric about the center. There are some fun sort of true-false questions that I can build around the fact that intervals of convergence are always symmetric about the center, like is -2 to 5 a possible interval of convergence for a power series centered at 0? No, because that interval is not symmetric about 0. So those sort of things are worth just remembering, right? There's a reason we call it a radius, because it's sort of the distance you can travel from the center and stay in that interval. Remember the way this works. I give you a power series. You run either the ratio test or the root test. That will give you an inequality that you then need to solve for x. Once you've solved that inequality, you can kind of sketch the center and the radius of convergence. You sketch the center and the endpoints. That'll tell you what your radius of convergence is. And then you test those endpoints. And we did plenty of that on Friday. So I'm not going to run back through those specific examples, but I will look at one or two kind of fresh examples where the power series are not exactly in this form, but you have some very important examples here today. So we did see last time that the interval of convergence can be open, right? If you have a geometric series, if your power series happens to be a geometric series, then you'll always have an open interval of convergence. We also had one example where it was closed on one side and open on the other side. And that was because when you tested those endpoints, when we we plugged in 1, the series converged. When we plugged in -1, the series diverged. All of that, of course, means that you're going to have to do about 3 convergence tests per power series, right? You got to run the root test or the ratio test to find the radius of convergence. And then you do some sort of test at each endpoint. The standard of like rigor that I'm going to hold you guys to as you test the endpoints, because I know nobody wants to write out all of the convergence test work for each of those things. When you run the root or ratio test, you got to show me all the work. And then you got to show me you solving the inequality. When you test the endpoints, I'll let you get away with just saying this converges or this diverges, but you got to tell me by what test. So converges by the alternating series test or diverges as a p-series, those sort of things. The next example I want to show you is a very famous one. So let's find the ROC and IOC for the power series sigma n from 0 to infinity x to the n over n factorial. This turns out is the power series for e to the x. In fact, in some classes, in some books, in some situations, you take this to be the definition of e to the x. The first few terms here look like x to the 0 over 0 factorial, that's 1, plus x to the 1 over 1 factorial is x, then x squared over 2, then x cubed over 3 factorial. Maybe I'll write these like this. 0 factorial, and so on. All right, so it's like 1 plus x squared over 2 plus x cubed over 6 and so on. I want to find the radius and interval of convergence. There's only one thing to do here. It's well, I guess we could run the root or ratio test. Because of the factorial, we definitely want to run the ratio test. And most of the time, pretty much all the time, you're going to run the ratio test. Ratio test says let L be the limit as n goes to infinity of the absolute value of an plus 1 over an, which here is the limit as n goes to infinity of the absolute value of an plus 1 is x to the n plus 1 divided by n plus 1 factorial. And then dividing by an means multiplying by n factorial over x to the n, multiplying by the reciprocal of an. And as is always the case with these, we're going to kind of group the similar terms together. So that's x to the n plus 1 over x to the n times n factorial over n plus 1 factorial. X to the n plus 1 over x to the n is just x. So this is lim n to infinity, absolute value of x times n factorial over n plus 1 factorial is 1 over n plus 1. We've done enough of that I don't feel it necessary. But if you're unsure how to simplify this, of course, you would write this out as n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. And this is n plus 1 times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. And the terms from the top cancel with the n minus 1 and so on from the bottom, just leaving the n plus 1. This is the same as lim n to infinity, absolute value of x times the absolute value of 1 over n plus 1. Let me come down here a little bit. All right, so the absolute value function is multiplicative, meaning if you have something times something else, all in absolute values, you can take the absolute value of each of them on their own and multiply those. And then since this absolute value x here doesn't have any n's in it, he is independent of the limit, he can come outside. So you get absolute value of x times lim n to infinity 1 over n plus 1. And I'm ditching the absolute values on the n plus 1 piece because 1 over n plus 1 is positive. N is going to infinity here. N just runs from 0 to infinity, so 1 over n plus 1 is always positive. What is this limit? The limit as n goes to infinity of 1 over n plus 1.
Zero.
Very good. As n goes to infinity, n plus 1 goes to infinity. 1 over infinity is 0. So we get here the absolute value of x times 0. And that's kind of strange. Remember how we solved all the examples from last time? At the end of this, we got L equals the absolute value of x times something, and then we set up some inequality. But this means L is less than 1 if and only if the absolute value of x times 0 is less than 1. So how do you solve an inequality like that? I want you to think about this for a minute. For what numbers x is the absolute value of x times 0 going to be less than 1?
Infinity.
Well, for any value of x, right? That's the idea. But absolute x times 0 equals 0 for all x. And 0 is less than 1. So L is less than 1 for all real numbers x. In other words, no matter what you plug in for x, since L equals 0 is less than 1 for all real numbers x, the interval of convergence is all real numbers, negative infinity to infinity. And the radius of convergence, and maybe this is what you meant by infinity, is r equals positive infinity. So in other words, this is a very nice power series. This power series converges absolutely no matter what number you plug in for x. And if you think about it a little bit, that's not a terribly surprising thing. The top here, x to the n, no matter what you plug in for x, is going to be harshly dominated by n factorial. In other words, no matter what you plug in for x, these terms will go to 0 very quickly. Quickly enough that even if you plug in 10 million for x, this series will converge. Again, just for your entertainment, I want to show you what it looks like as a power series converges. So I claim, although I cannot show it to you just yet, that this is the power series for e to the x. All right, let me reveal these slowly so they're less cluttered. Oh. So here is the original red curve, e to the x, and the very first partial sum of that series, just 1. Here's 1 plus x. And like we saw last time, the first partial sum, the sum out to x to the 1, is the tangent line. Here is that tangent parabola, or osculating parabola, it's sometimes called. Here's the third order approximation. Here's the fourth order approximation, fifth order approximation, and you see the blue and the red gluing together better and better the more terms we use. Right, and you see the more and more terms, the better and better the blue sticks to the red. Over here, it's really good. Over here, things aren't great, but as you use more and more and more terms, this blue will stick to the red for longer and longer, right? You see, like the blue I have below sticks to the red further than the blue from the fourth order approximation. So that's what it means to say your interval of convergence is all real numbers. There are two other series like this that are intimately connected to the e to the x series, and I'm going to do calculate the IOC for one of them now. This will be the last example we do like this, and then we're going to move on to section 11.9. I'm going to find the IOC and ROC for sigma n from 0 to infinity, -1 to the n over 2n plus 1 factorial times x to the 2n plus 1. I have no problem telling you this is actually the sine function. You could take this to be the definition of sine x. But right now we're just practicing the ratio test work. I mean, L is the limit as n goes to infinity of absolute value an plus 1 over an, which for this series is the limit as n goes to infinity of -1 to the n plus 1 over 2 times n plus 1 factorial times x to the 2n plus 1 plus 1. So that's an plus 1. And now I multiply by the reciprocal of an, which is 2n plus 1 factorial divided by -1 to the n x to the 2n plus 1. And you do need to be comfy with all of the factorial work and everything here, right? That's why we've done so much of that in 11.6. Simplifying. Two n plus 1 is 2n plus 3. And for the same reason here, I have x to the 2n plus 3 over x to the 2n plus 1. So everywhere I have a 2 times n plus 1 plus 1, I'm distributing the 2, and I get 2n plus 2 plus 1, which is 2n plus 3. So that shows up here inside the factorial, and also here inside the power. And I grouped all the like terms together. Some patterns emerge, right? This is the absolute value of -1 times. Now the 2n plus 1 factorial over 2n plus 3 factorial, I am going to write that out. 2n plus 1 factorial is 2n plus 1 times 2n times 2n minus 1. And then we go all the way down to 3 times 2 times 1. Right? It's the product of all the positive integers less than or equal to 2n plus 1. Which is 2n plus 1 itself, and then the number right below 2n plus 1, which is 2n. The number right below him, which is 2n minus 1, and you keep going until you get down to 1. 2n plus 3 factorial would be 2n plus 3 times 2n plus 2 times 2n plus 1 times 2n times 2n minus 1, all the way down to 3 times 2 times 1. And you see that there's a 2n plus 1 factorial hiding inside 2n plus 3 factorial. And then x to the 2n plus 3 over x to the 2n plus 1, you subtract the powers, 2n plus 3 minus 2n plus 1, that's just x squared. The negative 1 inside my absolute value here, he's going to disappear. He's no longer a part of the picture because absolute value of negative 1 is just 1. I can cancel all of this with all of this. So we get the absolute value of x squared times 1 over 2n plus 3 times 2n plus 2. And as before, the absolute value of x squared comes out, then n to infinity 1 over 2n plus 3 times 2n plus 2. Well, within this limit, the top is staying 1, but the bottom is going to infinity. So this limit is again 0. The absolute value of x squared, I could rewrite that as the absolute value of x with the square outside. Absolute values and powers, play nice. No harm in doing that. So L equals absolute value of x squared times 0, which is 0, which is less than 1, for all numbers x. Hence, as before, the ROC is infinity, and the IOC is all real numbers, negative infinity to infinity. So this power series also converges no matter what you plug in. And again, I'd like to look at the first few terms of the series. I'll hold here just for a second. Anybody who's writing. All right, let's do it. This is kind of like you just took the odd parts of the e to the x series. And I claim if you do that, take the odd parts of the e to the x series and then make them alternate, you do get the series for sine. We'll stop here. This is one of my favorite examples because it's really nice. I think you can see the convergence quite nicely here, and it converges in a really symmetric way. If you're trying to understand what power series do, this is a great one to look at. So here, red is the sine function, and blue is the order 1 tangent. The order 1 power series, which is the tangent line. Here's the next partial sum, and the next partial sum, and you see the blue sticking to the red really well. Here's the next partial sum, and next partial sum. And the more and more terms you use, the better and better things stick. The order 9, order 11, order 13. Really beautiful, right? So from like negative pi to pi, this order 13 power series is pretty much the exact same thing as the sine function. And what I want you to notice is that the convergence is centered at 0, which is the center of this power series. Now, sure, this is a 2n plus 1 power here, right? Instead of just x to the n, but it's still x minus 0 to the 2n plus 1. All this 2n plus 1 means is that there are only odd terms in this series. It's still a power series. Another way to think of it is that all the even coefficients are 0. This is just the cleanest way to write it. Okay, so that's enough of ratio testing power series, right? It really is just the ratio test. The catch is you at the end sometimes have to solve an inequality. And in the examples like we saw on Friday of last week, you may need to spend some time checking the endpoints after that. But today is a fun day, because today we're going to start talking about representing functions as power series. So there you saw the power series for e to the x, the power series for sine x. How the fuck do you figure out that that last thing is the power series for sine x? Well, the answer, the long answer is something called Taylor's theorem, and that's what we're going to get to on 11.10. The kind of gentler introduction is you start with geometric series, and then you fiddle with them. Sometimes that fiddling involves integration or differentiation of a power series. But in the simplest possible cases, it just means plugging stuff in. And I'll show you what I mean. So this is representing functions as power series. And today we're going to talk about how to integrate and differentiate power series, which is a big step. So I'll say recall, if the absolute value of x is less than 1, i.e. -1 is less than x is less than 1, then the power series sigma n from 0 to infinity of x to the n is 1 over 1 minus x. This was the first example we looked at on Friday. This is a function of x. So if I asked you the function f of x equals 1 over 1 minus x can be represented as the power series sigma n from 0 to infinity x to the n, right? It's the same thing, but only for x's between -1 and 1. This problem of starting with the function and coming up with the power series is called representing a function as a power series. That's it. Now, in this section, section 11.8, or sorry, section 11.9, we will be primarily using this as our starting point. The fact that sigma x to the n and 1 over 1 minus x are the same. I will call this the geometric series trick. Most generally, if u is u of x, some function of x, then 1 over 1 minus u can be written as sigma n from 0 to infinity u to the n. And you got to remember this. So the goal in this section, when I give you a function and I ask you to represent it as a power series, is to get your function into this form, 1 over 1 minus u. You might have some constants out front. You might have some other shit going on, but you want to get it into 1 over 1 minus something. Once you're in that form, you can write that as sigma that something to the n. So this is our geometric series trick. And the fun first example, let's say find a power series for f of x equals 1 over 1 plus x centered at a equals 0. If you move the center, you change the series. Right? And this series, this basic geometric series 1 over 1 minus x is centered at 0, right? X to the n, we talked about that last time, centered at 0. The interval of convergence, of course, is symmetric about 0. So if I want to find a power series for this function, I need to rewrite 1 over 1 plus x as 1 over 1 minus something. What's the something going to be here? I can write this as 1 over 1 minus what goes in the parentheses.
One over 1 over 1 plus x.
Also, that's what I have here, right? 1 over 1 plus x. And I want that to be equal to 1 over 1 minus something. So I'm just trying to figure out what I can put in here to make this whole thing equal to this whole thing.
Minus x.
Yeah, negative x, right? So that's my u. So I'm going to plug into this formula where u is negative x. This would be sigma n from 0 to infinity, negative x to the n. Now down the road, we're going to do lots of stuff with series like these, including integrate and differentiate them. It's important that before you do any of that, you rewrite this in the standard form for a power series, or as close to that as you can. In other words, simplify. Negative x all to the n is negative 1 to the n times x to the n. Because negative x is negative 1 times x, and negative 1 times x all to the n is negative 1 to the n times x to the n. So the center here is 0, and the coefficients are negative 1 to the n. That's it, you're done. Just found a power series for 1 over 1 plus x. The first few terms of this would be 1 minus x plus x squared minus x cubed plus x to the 4 minus x to the 5th, and so on. So 1 over 1 plus x can be written as this big, long polynomial, where it's just the increasing powers of x, like any geometric series, but the signs flip back and forth from positive to negative. It's just coming from this formula, plugging in negative x for u. Take a look at decimals. This guy's not going to converge as nicely as the sine power series because it's geometric, doesn't converge quite as quickly. But here's 1 minus x, 1 minus x plus x squared, minus x cubed, plus x to the 4, minus x to the 5, plus x to the 6, minus x to the 7, plus x to the 8, minus x to the 9. Right? And you see that between negative 1 and 1, where are we? Here's 1. The black actually does a really good job of sticking to the red. Here's the red, here's the black. So if, for example, I wanted to integrate this from So negative 1/2, 1/2. That's this time you can't do it. Always part solve double inequalities, including this inequality. Oh, I got to swap around. Sorry. There we go. So if I wanted to find the red area, the area under the red curve, I could find the area under the black curve. It would be the same. And that's the game. That's where we're going. But we just watched this series converge to this function, which is pretty exciting. The interval of convergence here, if we needed to find it, it's quite simple because I'm using my geometric series trick. So you may want to add to this that these geometric series, I mean, we know this, hopefully this is something you would remember, but if you're kind of thinking of this as your magic formula for this section, remember that you need the absolute value of u to be less than 1. So here I used u to be negative x. So here I need the absolute value of negative x to be less than 1. Well, the absolute value of negative x is the same as the absolute value of x. And that's the same as saying negative 1 is less than x is less than 1. So the IOC here is negative 1 to 1. And we don't check endpoints. We don't need to test the endpoints for geometric series. All right, geometric series always have an open interval of convergence. And again, that's what we saw, right? This thing only glues, the black only glues itself nicely to the red between negative 1 and 1. If you step away from that interval, all bets are off. Let's try another simple example like this.
Wait, Professor, can I see that last part again? 1 second.
Yeah, sure. Here we go. Oh, there it is.
Thank you.
Yeah, of course. All right. Let's find a power series for f of x equals 1 over 2 minus x, centered at a equals 0. Now, actually, let me change this to 9 over 2 minus x. How about that? Give us a little bit more feel. Again, my goal is to put this in the form 1 over 1 minus something. And there's more than one way to do that. But there is sort of a general approach. So when you see something like this, a rational function where the top is a constant and the bottom is linear, you can always play this game. First, I can pop the 9 off the top. That's the same as 9 times 1 over 2 minus x. And now the problem is the 2, right? I need 1 over 1 minus something. So can anybody suggest a way to turn this 2 downstairs here into a 1? Any algebra stuff I could do to make that 2 into a 1?
Multiply both sides by 1 over 2.
Yeah, I could like divide top and bottom by 2. That's one way to say it. I would say it like this. I would say I'm going to factor a 2 out from the bottom. Same result. So I'm force factoring a 2 out from the bottom. Then this 2 would become this 1. And the x would become x over 2. You see, if I distribute this 2 over these parentheses, I get 2 minus x back. So these really are equal to each other. My 9 is still chilling out front. Then the 2 can come out from the downstairs, making that 9 and 9 halves. And then I have 9 halves times 1 over 1 minus x over 2. So here's your u. That means this thing is 9 halves times sigma n from 0 to infinity x over 2 to the n. And again, I want to simplify. We always want to write this in the nicest form possible. So this is 9 halves sigma n from 0 to infinity. That's 1 over 2 to the n times x to the n. I'm just using basic algebra stuff here. X over 2 to the n is x to the n over 2 to the n. All right, so I'm not doing anything out here. Nothing with the 9 halves, nothing with the sigma, just x over 2 to the n. That's x to the n over 2 to the n. And I can split that up as 1 over 2 to the n times x to the n. Then I can bring the 9 halves back in. Remember your rules for series, constant multiples can come in and out, just like with integrals. That's 9 times 1/2 times 1 over 2 to the n times x to the n. And the 1/2 times 1 over 2 to the n, those can be put together. So I would probably write this as n from 0 to infinity, 9 over 2 to the n plus 1 times x to the n. So here is your power series in its nicest possible form. You've got your coefficients laid out right here and your x to the n right here. The center you can see is 0. The coefficients you can see are 9 over 2 to the n plus 1. And if I want to find the interval of convergence, because this is a geometric series, that will just come from the absolute value of u is less than 1. Well, what was u? It was x over 2. So this means that the absolute value of x over 2 is less than 1, which is the same as saying absolute value of x divided by 2 is less than 1, like this. And we can multiply both sides by 2. So you get -2 is less than x is less than 2, i.e. the IOC is the open interval from -2 to 2. And I promise you, you'll have to do this on the test. All right, there will be at least one problem where you need to use this geometric series trick and tell me the interval of convergence. It will happen. Questions on any of these steps? Questions on the interval of convergence? If we sketch the IOC, center is 0, the endpoints here, -2 and 2. So my radius of convergence would be 2. And neither endpoint is included in the interval of convergence because, again, geometric series automatically diverges at the endpoints. I'm going to do one more example like this, and then I'm going to introduce the calculus operations. So again, find a power series for this function. Here it's 1 over 1 plus x squared, centered at a equals 0. Most of the power series we're going to work with will be centered at 0. And again, the only thing I can do is try to write this in that form, 1 over 1 minus something. So 1 over 1 plus x squared can be written as 1 over 1 minus what?
Negative x squared.
Very good. This is the negative of x squared, like that, right? The square has to be inside the parentheses, otherwise the negative would go away. So that's your u. So this has to be sigma n from 0 to infinity, negative x squared to the n, which is sigma n from 0 to infinity. The negative gives you a negative 1 to the n, and then you have x squared to the n left over. And more just basic algebra rules, x squared to the n, everything else staying the same, x squared to the n is x to the 2n. And what do the first few terms of this look like? Right? So the IOC here is again absolute u less than 1. That means absolute negative x squared less than 1. That means absolute of x squared on the outside less than 1, which means absolute x is less than the square root of 1, which is 1. So negative 1 is less than x is less than 1, i.e. the IOC is the open interval from negative 1 to 1. All right, nothing exciting there. The first few terms of this series, make a little note here. One over 1 plus x squared. If I write out the first few terms of this series, sigma n from 0 to infinity, negative 1 to the n, x to the 2n. The fact that the power of x here is not just n, but is 2n, means that there's only even terms in this series. So this is like 1 minus x squared plus x to the 4 minus x to the 6 plus x to the 8 minus x to the 10 plus, and so on. If I look at the first few partial sums, right, this is that curve called the Witch of Agnasi. It's kind of cool. It's like a little bump curve. Classic problem from Calc 1 is to find the inflection points here and here. These things. Right, and you see the blue converging to the red only between negative 1 and 1 though, because that's my interval of convergence. Outside of -1 to 1, the blue is not even going to try to glue to the red. Within the interval -1 to 1, the blue will try harder and harder to glue to the red the more and more terms we use. If I add minus x to the 14, plus x to the 16, minus x to the 18, you'll see it's gluing a little bit further. It's coming a little bit closer to those endpoints. But because the interval of convergence is the open interval, -1 to 1, right at that endpoint, the blue will always run away from the red. The reason I wanted to write out this is to point out something interesting in the symmetry of the graph. Think back to the end of Calc 1. If you had to describe this graph, or even pre-calculus, what word would be useful to describe this function? What kind of function is this? Think graph symmetries. What kind of symmetry does this graph display? It's an even function. And the power series has only even powered terms. So power series for, yeah, it's symmetric about the y-axis. Thank you, Frank. Sorry, I didn't see that sooner. So the graph of the red function is symmetric about the y-axis, which means it's an even function. And it is true that an even function, when written as a power series, will only have even powered terms, right? 0, 2, 4, 6, 8, 10, 12. Those are all even powers. The other piece is also true, right? Yeah, also. An odd function power series will have only odd powered terms. Fun fact, you may have noticed that the power series for sine, right, that x to the 2n plus 1, sine is an odd function, and his power series only had odd powered terms. These are true facts in general. Okay. So 1 over 1 plus x squared can be written as sigma n from 0 to infinity, -1 to the n, x to the 2n. There's one function that I've told you guys over and over again in this class that I just love. And that is the inverse tangent function. So now we're going to talk about integrating and differentiating of power series. This is a topic that intimidates many people, but it's really not that bad. I'm going to show you an example first, and then I'm going to give you the theorem. First example here. Find a power series for f of x equals the inverse tangent of x. And it will be centered at 0. Here's what we're going to do. We're going to begin with the fact that we just discovered 1 over 1 plus x squared is equal to sigma n from 0 to infinity, -1 to the n, x to the 2n. And we're going to integrate on both sides with respect to x. On the left-hand side, when I integrate 1 over 1 plus x squared, I will get the inverse tangent of x. And on the right-hand side, when I integrate with respect to x, I will get a new power series. And that new power series will be the power series for the inverse tangent function. So here we go. Integral 1 over 1 plus x squared dx. That's the integral of the left. Equals integral sigma n from 0 to infinity, negative 1 to the n, x to the 2n dx. And writing things like this on a whiteboard is a great way to scare Calc 1 students. You got a friend taking Calc 1, you want to scare the shit out of them, go ahead and put this on the board. But it's really not that bad. See, here's the deal. The integral is a dx integral. The sigma and the negative 1 to the n, those don't have any x's in them. The only x's are right here. This is a power rule integral. So the sigma and the negative 1 to the n can be treated like constants. And you just need to integrate the x to the 2n, which is x to the 2n plus 1 over 2n plus 1. And on the left-hand side, I will write the inverse tangent of x. And now I'm doing an indefinite integral, right? So I get a plus c. Technically, you get a plus c on both sides, but we only write it on one side. You're used to thinking of the integral of this as being inverse tangent of x plus c. And on the right-hand side, we just ignored all of this stuff and did the integral of x to the 2n, which is a power rule integral. You add 1 to the power and divide by the new power. So integral of x to the 2n dx is x to the 2n plus 1 over 2n plus 1. And technically there'd be a plus c here, but since there's 1 on the other side, I just leave him. We've just done all the hard work. Now, we need to find c. If I plug x equals 0 on both sides, I get the inverse tangent of 0 plus c equals this piece. When you go to plug 0 into this series, you should write out the terms. So this is, when n is 0, you get 1 times x over 1. And then you'd have minus x cubed over 3, and then plus x to the 5 over 5, minus x to the 7 over 7, and so on. And all of this is evaluated at x equals 0. The reason you should, anytime you're plugging the center into a power series, the reason you should write out the terms, remember when we talked about plugging the center into a series on Friday of last week? You don't necessarily get all of the terms to be 0. You get all the terms with x's in them to be 0. So it's possible that there was a constant term out here that wouldn't be 0. But in this case, we really do get 0. So the inverse tangent of 0 is 0 on the left.
Can I ask how you got that?
This?
Oh, yes.
I'm just writing out the first few terms of this series.
Okay, so you just plugged in 0 for all n's?
I plugged in 0 for n, and that gave me this.
All right, thank you.
And then I plugged in 1 for n, and that gave me this. And 2 for n gave me this. So like this is the n equals 0 term. This is the n equals 1 term. This is the n equals 2 term. This is the n equals 3 term, and so on. Yeah, no worries. These are good things to ask. So now on the left-hand side, inverse tangent of 0, that's 0, so I just have C. And over here I have 0 minus 0 cubed over 3 plus 0 cubed to the 5 over 5, and so on. All of this is 0 as well. So C really is just 0. So the inverse tangent of x really is just sigma n from 0 to infinity, -1 to the n, x to the 2n plus 1 over 2n plus 1. And I would say this is the next power series that you need to remember forever and ever on. So that geometric series trick, that's one of them. That's one of the power series that I expect you to commit to memory. This is the next one. There will be several more. I'm going to cook up one more of them for you now. Actually, no, let me go ahead and give you the theorem. So differentiation and integration of power series. Examples are nice, but let's look at the theorem before we do the next example. Oh, hang on. Sorry. Pause for just a moment. The interval of convergence for this, a fun fact. The series we started with, we knew had IOC -1 to 1, open interval -1 to 1. When I integrated on both sides, something happened to that IOC. Look at this series. If you plug in +1, this series will now converge. You would have -1 to the -1 to the n over 2n plus 1. That series is convergent by the alternating series test. And if you plug in -1, the series will also converge. This now has a closed interval of convergence. You should check that yourself. So something cool happened. When we integrated this series, we made its IOC larger. The IOC of the series we started with was the open interval from -1 to 1. Didn't include either endpoint. This series converges both at -1 and at +1. So when you integrate a series, you can pick up an endpoint. That's pretty cool. And I'm going to describe that in general in the theorem. So now we're ready for this. If f of x can be written as a power series sigma n from 0 to infinity Cn x minus a to the n, then I can find a power series for both the integral of f of x dx and a power series for f prime of x. This would be the integral of that series. Which is some constant plus sigma n from 0 to infinity Cn times 1 over n plus 1 times x minus a to the n plus 1. You add 1 to the power and divide by that new power. It's the same old power rule. And the similar result for derivatives is if you differentiate that power series, n from 0 to infinity, Cn x minus a to the n. You're going to apply the power rule again. All right, the power rule for derivatives this time. Now I'm leaving this blank for just a minute. Do the same. This will be Cn times n times x minus a to the n minus 1. When you differentiate a power series, it is possible that the starting term is going to go away. And this is the way it's described in the theorem, that this index shifts from 0 up to 1. Because the very first term of this series is C0 times x minus a to the 0. It's just C0, right? This series is C0 plus C1 times x minus a plus C2 times x minus a squared plus and so on. That very first term, the n equals 0 term, is a constant term. And when you differentiate a constant, it goes away. So this is the theorem. And I'm going to make some notes. When integrating a series, we can pick up endpoints in the IOC, like we saw with the inverse tangent series. We started with a series that had an interval of convergence, which didn't include either endpoints, open interval -1 to 1. And when you integrated, you get a power series that had a closed interval of convergence, did contain both endpoints. Also, when differentiating a series, we can lose endpoints. You might go from having a closed interval of convergence to an open interval of convergence, or maybe you just lose one of them. Finally, when you differentiate a power series with a constant term, which has a constant term, the starting index bumps up by 1. So like that's the n equals 0 here becoming an n equals 1 here. Now I understand that this theorem looks scary. So I want to show you why this is true by writing out the terms of the series and then integrating or then differentiating. So a quick proof. I know proofs usually intimidate and obfuscate at this level. I promise you this is not one of those. The integral of f of x dx is the integral of the series sigma n from 0 to infinity Cn x minus a to the n dx. If I write out that series, that's C0 plus C1 times x minus a plus C2 times x minus a squared plus and so on dx. All right, here's the n equals 0 term. Here's the n equals 1 term. Here's the n equals 2 term. If you make the substitution, u equals x minus a, then du is just dx. This becomes the integral of C0 plus C1u plus C2u squared plus and so on du, which is capital C, your new constant from the integral, plus C0 times u plus C1 times u squared over 2 plus C2 times u cubed over 3 plus and so on, which is capital C plus C0 times x minus a plus C1 times x minus a squared over 2 plus C2 times x minus a cubed over 3 and so on. And then if I rewrite this in sigma notation, I've got my capital C out here. And then what is this series? It's sigma n from 0 to infinity Cn times x minus a to the n plus 1 over n plus 1, which is the same thing as C plus sigma n from 0 to infinity Cn times 1 over n plus 1 times x minus a to the n plus 1, which is exactly what our theorem said. So the integral of a power series really is the thing we thought. And the way you get there is just integrating term by term. You just integrate each of these pieces the same way you would integrate anything else. You do a little u sub, and then you bump the power up and divide by the new power. What about the derivative? The derivative of f of x would be the derivative of that power series which is the derivative of, we just write out the series, C0 plus C1 times x minus a plus C2 times x minus a squared, and so on. ddx of C0 is the derivative of a constant. That's 0. Plus ddx of C1 times x minus a, well, that's just C1. Plus the derivative of C2 times x minus a squared is C2 times 2 times x minus a to the 1 by the chain rule. The next term in here would have been plus C3 times 3 times x minus a squared, again, by the chain rule, right? The next term here is C3 times x minus a cubed, and so on. So if I rewrite this in sigma notation, the n equals 0 term is gone. My new series starts with the n equals 1 term. And what we have is Cn times n times x minus a to the n minus 1 as promised. So you see why it's the case that the starting index can bump up when you differentiate a power series, because this n equals 0 term is constant, it can go away. And that's that note, that if you differentiate a power series with a constant term, the starting index bumps by 1. All right, this is the end of the proof. I know we are just about at the end of class, but I'm going to give you some homework that I want you to be able to get started on that involves differentiating power series. So I want to do an actual concrete example, and then I'll let you go. I'll say differentiate 1 over 1 minus x to find a power series for f of x equals 1 over parentheses 1 minus x squared. So let me first just take a look at what the derivative of 1 over 1 minus x is. That would be the derivative of 1 minus x to the negative first power, which by the chain rule is negative 1 times 1 minus x to the negative 2 times negative 1. So this negative 1 comes from the chain rule. It's the derivative of the inside. And I've just applied the power rule to the outside. Bring down the power, reduce the power by 1. And what is that? Well, it's negative 1 times negative 1 is positive 1. That's 1 minus x all to the negative 2, which is this function 1 over parentheses 1 minus x squared. So if I start with a power series for 1 over 1 minus x and I take its derivative, that will give me the power series for 1 over parentheses 1 minus x squared. In other words, the function I want, which is 1 over parentheses 1 minus x squared, is the derivative ddx of 1 over 1 minus x. And I know the power series for 1 over 1 minus x, that is sigma n from 0 to infinity x to the n. And by my theorem, ddx of sigma n from 0 to infinity x to the n is sigma n from 1 to infinity n x to the n minus 1. That's it, we're done. All right, I'm going to go ahead and wrap it up here. You'll have a new homework set opening up today where you will be using the geometric series trick to find power series. And there will be some problems where you will integrate and differentiate to find power series. Don't be intimidated by this. You can do it. It's really not that hard. You do need to remember how to integrate and differentiate the terms of the power series, because that's really all that's going on. You're just integrating one term at a time or differentiating one term at a time. Being able to write down the result in sigma notation is kind of the trick. And just follow the theorem. It will work fine for you, I promise. If you get stuck on any of these, you can come see me in office hours, or you can send me a Canvas message, any of that stuff, all the same stuff that we've been doing. Next time, I will do a little bit more practice with this. I'm going to cook up the series for the natural log function for you. That'll be fun. And then we're going to move into something called Taylor's theorem. So on Wednesday, we're going to talk about Taylor's theorem. But for now, I want you to practice this 11.9 stuff using the geometric series trick and integrating, differentiating to get new power series. That's it from me for today, guys. I hope you have a lovely rest of yours, and I will see you on Wednesday.